Okay, today I'm going to see the topic name is um, AM modulation, AM generation. So AM modulation, we already saw that. So in the AM modulation, we have to see generation of AM modulation. So before start the topic, we have to see about types of filter. Because if you want to see generation of AM or whatever the next topic, so you should be know about the topic about filters. So here there are four type of filter as are present in communication field. One is low pass filter, another one is high pass filter, then band pass filter and band stop filter. So low pass filter. So what's a low pass filter? So it allow low frequency component and it will be reject the high frequency component. That means it will be pass only low frequency components and it will be eliminate high frequency component. So that is called as low pass filter. Similarly, high pass filter, yeah, it can only pass high frequency component and it eliminate the low frequency component. So only high frequency only passed through this filter and low frequency it won't pass through this filter. This is called as high pass filter. Okay, so what about band pass filter? So band pass filter it only allowed desired bandwidth. That means the particular bandwidth only allowed. The remaining even the low or high whatever it may be, the remaining thing will be rejected by band pass filter. The band stop filter it's the opposite of band pass filter. So band stop filter it will be reject the particular band and it will be allow remaining the rest of the bands. Okay, so that is called as band stop filter. So these are the types of filter in DSP applications, digital signal processing. And now we are going to see AM generation. So AM generation, uh, yeah, we already see AM modulation. So in that there are the input we are giving modulating signal and we given another input as name as carrier signal, and finally we got the modulated output. But here we want to generate the AM waveform. Then these are the device following device we have to use. The number one is square law modulator and number two is switching modulator. So square law modulator, see that. Uh, so there are two input we are using. Then black contains square law device and band pass filter. So that's why we already just know we saw types of filter. So we know already the about band pass filter. So now we are going to see how the AM generation that waveform will be generated through the square law modulator. So square law modulator, it has a two type of input. One is modulating signal, that is our message signal. Another one is carrier signal. So modulating signal or message signal that is sent to input of square law modulator, that we can say mathematically represented as AM cos 2 pi FMT. And similarly the another input we can say that is carrier signal AC cos 2 pi FCT. So this signal output V1 of T is sent to square law device. So square law device, it will be uh, you know square that signal. If you see the mathematical representation you will be easily understand. Then it will be square the signal, then the signal coming to the output of V2 of T. So after that, the band pass filter it will be cut that particular band or particular frequency. That means particular desired band will be only allowed. The remaining thing will be cut by band pass filter. So, for example, if you see, that mathematical representation, we can easily understand about square law modulator. Before that, example, if The frequencies are maybe high frequency, low frequency, whatever it may be. Particular band or particular education will be allowed. The remaining will be eliminated by band pass filter. Finally, you will be get it a softy. That is AM generation waveform. Okay, so this is square law modulator operation. And mathematically represented as uh, in the diagram it says v1 of t and v2 of t. So we know v1 of t, so v1 of t mathematically represented as it's a combination or summation of two input m of t and carrier signal. So m of t plus, that means summation means that we are adding two signal. Okay, so m of t plus AC cos 2 pi FCT. So, so we know that M of t is message signal, AC cos 2 pi FCT is a carrier signal. So this signal we can consider as a V1 of t. Then V1 of t applied to the that square law devices. So after that the output get it from V2 of t. So K1 and K2 is a constant value. We get it V1 of t. Then plus the output of V2, that means output of square law device we got V1 square of t. That means the input we are giving V1, that will be squared by square law devices, then output you get it from V1 square of t, where K1 and K2 are constant. So here we know already V1 of t equation. So in that V1 of t equation we have to substitute in V2 of t equation. So V2 of t equation we already know K1 V1 of t plus K2 V1 square of t. So in that we just substitute V1 value of equation. So if you substitute, you will be getting the equation like this. Then V2 of t is equal to K1 m of t and Kc cos 2 pi fct and K2 m of t plus Ac cos 2 pi fct whole square. So this is the equation we got it. So we just multiply this constant value into the equation. So if you multiply, you will be get the equation like that. So K1 m of t plus K1 Kc cos 2 pi fct plus K2 m square m of t. So similarly, the equation is going like that. And again, we have to simplify the equation. And V2 of t equal to K1 m of t plus, and so we already know the formula a plus b whole square is equal to a square plus b square to ab. So based on that formula, we have to simplify the equation. So this two, so K1 and AC and 2 km. So this is similarly like the this one, a plus b whole square is equal to a square plus b square is equal to 2ab. So we have to change the equation like that. So k1 m of t plus k2 m square of t. So this is a square b square, So this is a square and this one is considered as a b square and 2ab like that. Okay, k1 ac plus 1 plus 2 kb k1 m of t cos 2 pi fct. So finally, if you simplify the equation, you get it V2 of t is equal to K1 m of t and K2 m square of t plus K2 AC square cos square 2 pi fct plus K1 AC 1 plus 2K2 divided by K m of t cos 2 pi fct. So this is the final equation we got. But first term of above equation, it is really unwanted because that is not a AM waveform. So that equation, neglected by bandpass filter. So if you apply the bandpass filter, the first three equation eliminated by bandpass filter, and finally we get the equation K1 AC 1 plus 2K2 divided by K1 m of t cos 2 pi fct. So this is the equation is AM generation waveform. So see that, so S of t is equal to, you got this equation. So here we have the Ka, maybe it's amplitude sensitivity. So as 2K to 1, 2K2 divided by K1. So for standard AM equation, if you put it as a amplitude sensitivity, then AC plus 1 plus Kam of t cos 2 pi fct. So this is the final equation of square law device. And next one is switching modulator. Okay, so switching modulator, yeah, so there are two input we have to give, M of t, C of t, AC square. Similarly, here also we have to give two input. Then here we have switching divide and band pass filter, then V1 of t, V2 of t, S of t. So switching modulator is similar to the square law modulator. The only difference is square law modulator, it's a non-linear mode. The switching modulator it can operated as a ideal switch. Okay, so V1 of t equal to M of t plus C of t. So that is the equation we know. Similarly, same like previous generation square law modulator. So switching modulator also having this two input, same input, M of t and C of t. So we know that modulating signal considered as M of t and carrier signal is considered as a C of t. So M of t plus C of t we can say as AC cos 2 pi FCT. Okay, then V1 of t, again we have to simplify the equation. V1 of t is equal to M of t plus C of t equal to M of t plus AC cos 2 pi FCT. So the signal, that V1 of t applied as an input diode. Also that carrier signal. Uh, so based on the carrier signal, the diode will be on and off. Okay. So carrier signal control the diode. It is on and off. If the carrier signal is more than zero, the diode getting on. If it is less than zero, the diode get is off. So therefore, the equation we can say V2 of t equal to V1 of t 0. Then if the carrier diode is more than 0, that the equation we can say V1 of t. Similarly, V2 of t equal to, if the carrier waveform is less than 0, then the value is 0. So we can approximately we can say the equation V2 of t equal to V1 of t and X of t. So there is equation 2. This is similarly like periodic pulse train. So if you can write the equation like that, x of t equal to 1 by 2 plus 2 divided by pi. So 8 summation of n is equal to 1. So minus 1 n 2. So if you write the Fourier transform equation, then you will be get like this. So x of t is equal to 1 by 2 plus 2 divided by 2 cos 2 pi fct minus 2 divided by 3 by cos 6 pi fct. Okay. So this is the equation you got it from Fourier transform equation. So we substitute this v1 of equation 2 and x of v1 of t and x of t valuation equation to second equation. Where is second equation? So this is the only second equation. So in that equation we have to substitute v1 of t and x of t. So if substitute, you will be getting this equation. Finally, you still simplify, and you got the equation like this. So in that equation, the first term is the represent that is desired one. The remaining terms is unwanted. So that term eliminated by similarly same band pass filter. So that band pass filter eliminating except first term, the remaining term will be eliminated by band pass filter. And finally, you got the equation S of t is equal to AC divided by 2 1 plus 4 by AC m of t cos 2 by FCT. So we know the standard equation of AM wave. So S of t AC 1 plus Ka m of t cos 2 by FCT. So Ka we know that amplitude sensitivity. So the remaining equation comes like that. Okay. So this is a generation of AM waveform. Okay, thank you.